Alright, so here we are, Chapter 9, and because we skipped Chapter 4, we're going to pick up a little bit of information from Chapter 4 as well. But today is primarily going to be on translations, 9-1. So we have some vocabulary. The first term, congruent polygons, comes from Chapter 4 in 4.1, and the vocabulary words in 9.1, we have transformation, pre-image and image, rigid motion, translation, and a composition of translations. So we'll be getting to those definitions all when we start talking about 9.1. So section 4.1 is congruent figures. And the essential learning for this section is that we can determine whether two figures are congruent by just comparing corresponding parts. Corresponding parts would be corresponding angles and corresponding sides. So congruent figures have the same size and shape. They're exactly the same size and shape, but their orientation can be different. When two figures are congruent, you can slide, flip, or turn one so that it fits exactly on the other one. So a slide means an object can be simply slid up to a new position. So a flip means that an object can be flipped around, like so. And a turn is when an object is turned or rotated like such. So these three different types of transformations all have specific words, which we'll talk about throughout this chapter. Today we're going to be talking about this one, the slide, which is also called a translation. So we'll come back to that vocabulary. Alright, we have our first vocab word, congruent polygons, and also our first key concept. So congruent polygons are polygons that have corresponding parts. They're matching sides and angles that are the same size or the same angle measure. So if we look at the example here, the picture, angle A is congruent to angle E, B and F are congruent, D and H are congruent, C and G are congruent. But it's not just the angles, the corresponding sides are also going to be congruent. So length AB is the same length as EF, and DC and GH, and so forth. We can see those corresponding parts listed right here and here. Here are the sides, corresponding sides. Here are the corresponding congruent angles. And what we have right here is our congruent statement. So again, that is our congruent statement. It states which polygons are going to be congruent. And it is important to make sure that we get the corresponding vertices matched up. So for these examples, we are told that the triangles are congruent. So we don't have to try to prove they're congruent. That comes later. We just want to write our congruent statement, or finish our congruent statement. When we do this, the first triangle, we can name it any way we want, and I prefer to write it alphabetical. So the first triangle is ABC. So ABC is going to be congruent to triangle, and now we need to match up corresponding vertices. So it's going to be A is going to correspond with A. And we went A to B, so that means we're going to go A to D. And last we end with C. So we have triangle ABC is congruent to triangle ADC. In the second example, angle A is this really skinny angle. It's going to match up with angle L. And then B, we go down this side, so that's going to be J. And then C is going to correspond with K. And the last one, ABC, this time these two triangles look like they are orientated the same way. So ABC is going to be congruent to RTS. So again, we just need to make sure that we have our corresponding vertices matched up. So here are a couple more examples on congruent parts and congruent figures. So the first example, quadrilateral HIJK is congruent to quadrilateral LMNO. And so we can look at the corresponding sides. HI is going to correspond with LM. Now sometimes it's a little hard to get it from the picture. So we can also get our corresponding congruent parts from our congruent statement. So notice HI is the first two letters here, and LM are the first two letters here. Therefore, those are congruent corresponding parts. Similar, IJ and MN, JK and NO, and HK and LO, or OL. Likewise, our angles, angle H is going to correspond with angle L, I with M, J with N, K with O. So even though we have the picture, we can also write all that stuff from our congruent statement. So the next example does not have a picture, and so we need to come up with the congruent corresponding parts just from our congruent statement. So let's start with the sides, and we could say side WY is congruent to MK. So WY, use correct notation, is congruent to MK. And likewise, we can finish off the other statements as well. Let's go ahead and do our angles. So we've got angle W is congruent to angle M, W and M. And angle Y is congruent to angle K, so angle Y is congruent to angle K. And last, angle S is congruent to angle V, angle S is congruent to angle V. So that pretty much wraps up the information we need from Chapter 4 at this point. And now we're going to go on to Chapter 9. And so here we are, Chapter 9.1, Translations. And we're finally there. Our essential learning from this chapter is that you can change the position of a geometric figure so that the angle measures and the distance between any 2 points of the figure stay the same. So in other words, we can change position, but the figures are still going to be congruent from its original to its ending statement. And remember, translations, as we'll look in this section, translations are a form of a transformation. There will be 3 different forms of transformations we'll talk about. Translations is the first one. So again, here's our vocabulary for this lesson. In this lesson we have transformation, pre-image and image, rigid motion, a translation, which is what this section is about, and then composition of transformations. So let's start with some of our vocab. Transformation. Transformation of a geometric figure is a function or a mapping that results in a change in the position, shape, or size of the figure. One example where you might see a transformation is in the game of dominoes. When you play dominoes, oftentimes the pieces are moved. So a domino can flip over, so flip upside down. Or the domino might slide to another position. Or the domino could be turned or rotated. In the game of dominoes, you can't change the size of these dominoes, and that's similar to what we're going to be doing in this chapter. We're not going to be doing any transformations in this chapter where the size changes, but there are some transformations that deal with that, and we'll talk about those later. So in a transformation, the original figure is called the pre-image. So in each of these cases, this is the original figure, that would be the pre-image, and this would be its image. The pre-image, and the arrow shows you the direction to its image, the pre-image and the image. So the figure that you end up with is the image. And you can always think about that as a mirror. If you look in a mirror, then you yourself are the pre-image, and what you see as your reflection is the image. So when we have transformations that preserve distance, those are a special kind of transformation where distances and angles are preserved. That means we keep basically the exact same shape, the exact same size. We might just change the orientation. If that is what is happening, then we call that a rigid transformation. A rigid transformation is a transformation that preserves distance and angle measures. And basically what that means is the image and the pre-image are exactly the same shape and size, and you could take one and put it directly over the top of the other one. All right, here are some examples where we're supposed to decide whether the transformations appear to be rigid motions. Again, rigid motions means that the size does not change. So our first example, if we trace the pre-image and then we check that with the image, you see that they are the same shape and size. So A does appear to be a rigid motion. Likewise, B, if we trace B and we check it, well, we could actually just check sides. Those are corresponding sides, they're the same length. Those are corresponding sides the same length. And if we were to turn this, then we could see that those corresponding sides are the same length as well. Likewise, we could check the angles if we wanted to. So again, B does appear to be a rigid motion. Let's look at C. On C, we don't have the words pre-image and image, but we have a notation that we can use. So here we have EFGH, quadrilateral EFGH, and this arrow here means it goes through some sort of a transformation. And it gives us, we say E prime, F prime, G prime, H prime. The prime is simply like an apostrophe, and the prime or the apostrophe means that it is the image. So, on our example here, EFGH is our pre-image, and E prime, F prime, G prime, H prime is our image. That's our resulting or our ending value. And again, we can see that those two shapes appear to have the same size, so we say that they are a rigid motion. In our last example, it becomes pretty obvious that these are not going to be the same size. So they would not be a rigid motion. So again, A, B, and C were rigid motions, but D is not a rigid motion. So like always, we need to be careful of notation. Notation is really important. So earlier we talked about this arrow notation. That just means that we have a transformation that maps every point of a figure onto its image, and it can be described with the arrow. The prime notation, apostrophe, is sometimes used to identify image points. So in this diagram here, K prime is the image of K. So here's K prime. That means K is our original or the pre-image, and K prime is the image. Likewise, J is the pre-image, and the image of J is J prime, and Q's image is Q prime. And so we could say triangle JKQ maps, that's the arrow, to triangle J prime, K prime, Q prime. Or we can, instead of using the arrow, we could say maps onto. Also, again, notice that the corresponding vertices must be in the same order. So when we have mapping, J to J prime, K to K prime, Q to Q prime. So 9.1 is really about translation. And translation is a type of transformation. It's the first type of transformation we're going to talk about. And so don't get these two words confused. A translation is a type of transformation. Words sound very much similar. And a translation is simply a transformation of a slide, or something slides somewhere else, but it keeps the same orientation. So, in our example right here, notice it slides over our image, our pre-image slides over to our image, but there's no rotation, turning, or changing of size here. It's just a direct slide over. That's a translation. And the notation we use to say that we're doing a transformation or a translation is a capital T. So the translation of triangle ABC is equal to triangle A prime, B prime, C prime. So a translation is a rigid motion, does not change shape or size. And notice what's unique about translations is that if you were to take the length from any point to its image, so B to B prime, A to A prime, C to C prime, those lengths would all be congruent. That's what it's saying right here. A to A prime is equal to B to B prime is equal to the length of C to C prime. So some more on notation is, here's our T, stands for transformation. This is sometimes called vector notation. And what we're doing is, if you think of this as like an X and a Y. So if we take each of our point and X and a Y, this means we're going to move it in the X direction, -2 spaces, and the Y direction would be -5. So in this problem, we're supposed to graph the image of triangle PQR. So let's see what that would look like. We can start with any point. Let's start with R. We're going to go -2, -2, and then -5. 1, 2, 3, 4. I'll come down here. There's a little more room. So point Q, 1, 2, 1, 2, 3, 4, 5. And as you go ahead and label these, this is going to be R prime, this is going to be Q prime. Now we just have to find P prime. So from point P right here, we're going to go 1, 2, 1, 2, 3, 4, 5. So there's P prime. Now we can go ahead and draw in our figure, and this is our image. Our image is going to be triangle P prime, Q prime, R prime. Notice I want to get the orientation the same, PQR. So here we're with that same example from what we just looked at. And here's the picture that we came up with. And if you were to look at the vertices, then transformation of point P is going to map to P prime at 0, -4. Transformation of point Q, basically all we have to do is subtract 2 from the X and subtract 5 from the Y. And we get 1, -2. And likewise with R, we get -3, -2. The way that they showed this example was they found the points first and then they graphed it. So let's now talk about composition of transformations. Composition of transformations just means there are 2 or more transformations. In a composition, you perform each transformation on the image of the preceding transformation. So here's an example of a composition of transformations. And if we're looking at our hockey puck at here, and we go through 2 different transformations. First it goes from 3 to 9, and then from 9 up to 5. That's the same result as if it had gone directly from 3 to 5. So let's look at another example. We're going to perform 2 transformations or 2 translations on quadrilateral PQRS. So first of all, we need to sketch P prime, Q prime, R prime, S prime from this transformation, where every point is going to go 8 in the positive X direction and -2 in the Y direction. So here we go, P positive 8 in the X direction and -2 in the Y direction. That is the same result as if we had gone straight here along the black line. So again, that's going to map. Here we have our P prime, Q prime, R prime, S prime. Now we're going to take that through another transformation. Transformate it from -3, 4. That means we're now going to go -3 in the X direction and +4 in the Y direction. So we could pick a different point this time. Let's go ahead and start with R prime. We're going to go -3 in the X direction, 1, 2, 3, and then +4 in the Y direction. And we end up with this point right here. Likewise, we could do that with all the points. And we get this purple shape that I have here. And notice now the points are labeled as P double prime, S double prime, R double prime, and Q double prime. Now we can look at what the transformation would be if we just did one translation that incorporated both of these at the same time. And let's look at our picture. And we could start, let's look at r. r to r prime goes right here. So r to r prime, notice that's 5 in the x direction and 2 in the y direction. So that could be rewritten as a transformation of 5 to comma 2, that's 5 x direction, 2 y direction, of p, q, r, s. That's going to translate to the p prime, q prime, r prime, s. Actually, these should be double primes. That's our resulting figure. And so when we do two transformations, you might have noticed that if I was to add the x values together, 8 plus a negative 3 does give us 5, and a negative 2 plus a 4 gives us a positive 2. So I could actually add the x change and the y change to get the composition transformation.